So good morning, everyone. My name is Charles McRobert. I'm from South Africa. I teach at Stellenbosch University, which is a university just outside Cape Town. And I will be chairing this session, this first session of the day, session A, and let me just make sure I get the name correctly. Coursework, laboratory, field, project-based, and numerical methods. And yeah, I think this is a really exciting conference. And yes, maybe some new ideas, some old ideas will be presented as new. And there will be a lot of educational buzzwords. I hope you have your bingo cards ready. But I think what's exciting about this conference is that everyone presenting a paper today has worked hard at developing their geotechnical teaching practices. And I think that's something that really needs to be celebrated, because although we still see failures in geotechnical engineering, all the tools are there to solve them. And for me, I think the real solution to reducing the number of failures, and that's not just failures when things fall down, but things that are built too strongly, is by better teaching, not necessarily better research. So we're going to have slightly fewer presentations. Two of the presenters were unable to make it, but we still have a very tight program. So when you get to 8 minutes, I dug out a harmonica from a back cupboard in my room, which wasn't very clever because my kids got hold of it and want to play it all the time. But when you have 2 minutes left, I will play my harmonica and give you a heads up that your time is almost up. So without further ado, I would like to welcome Katarina Kluge to talk to us about escape rooms.
Bonjour, monsieur, dame. Hello, everybody. I'm happy to be here at this conference for the first time. And I'm happy to present the escape rooms my colleagues Ansgar, Christoph, and I developed in the last years. So let me start with this. Look at these pictures. There are 4 people locked in a room. It's a team-based adventure game, and they want to escape from the room by solving several tasks. They feel a certain pressure because it's a time-limited challenge. They have to solve difficult tasks, and they have to solve it mentally or physically. They need creative thinking to solve all problems. They experience intrinsic motivation because they really want to solve everything correctly. And they feel satisfaction when they win the game. So now let's turn to the academic challenges. This is the situation lectures often look like. So a bit different from the atmosphere in an escape room. Of course, students' everyday lives should not feel like a never-ending escape room, edu-escapes as they are named in the academic field. But why not combining academic content with game-based learning? Why not inventing puzzles to course content like laboratory tests? Why not promoting active and collaborative learning and stimulating intrinsic motivation? An edu-escape not only reinforces subject knowledge, but can also further develop soft skills like communication and teamwork. And so Ansgar, Christoph, and I decided to develop edu-escapes to liven up our standard laboratory classes. When designing an edu-escape, you have to make several decisions. For example, which laboratory test do you want to include in the escape game? What learning objectives should the students reach after the game? What kind of structure should your edu-escape have? What's the ideal group size, smaller groups or larger groups? And for which time frame do you want the edu-escape? To answer those questions, a student of mine 1 year ago conducted a survey among 92 professors at universities in Germany, Austria, and Switzerland. We wanted to know which were the most common tests that are carried out in the laboratory courses. The ones in green are the ones that were mentioned most. The sieve analysis, the plastic and liquid limit, Proctor test, sedimentation, and density for maximum and minimum compactness. We also asked if students conduct their laboratory tests independently, and 75% of the professors said yes, they do. And 85 professors were interested in using Eduscapes. So we defined learning outcomes for the Eduscapes. Those are technical skills, like students are able to carry out soil mechanics lab tests independently, evaluate measurement results from lab tests or derive soil parameters and so on. But also social skills like work in a team, communicate, work under time pressure. I want to give you an insight now in the Eduscapes we designed by 2 example tasks. In my Eduscape, which is for 60 minutes, people come to the laboratory and have to find the starting point. They find it on a table, it's this paper, and at first glance they don't know what to do, but then they can read, for example, percentage of grain size smaller 0.2 millimeters. They have to realize that if they want to know that, they have to do a sieve analysis, and they have to go to the sieve analysis setup. There they find the data sheet, which you see here, with the retaining masses of soils in the different sieves. But one is missing. Instead, there is the sieve of the mesh size with 0.2 millimeters next to the data sheet, and there is soil inside. So they have to pour the soil into a pan, then weight the pan with and without soil, calculate the difference, and then enter the value in the data sheet. If they did this, they can calculate the retained fraction and the passing fraction as well. And if they do everything correctly, they have 1% of passing fraction for the 0.2 millimeter sieve. And this is the first number they can enter in this equation. You see, this is an equation with several numbers they have to find out. So students do not perform the full sieve analysis, but only one task, but they understand and recall how the sieve analysis works. After some more tasks, they come to this one, where they read poorly graded sand 2, well-graded gravel with sand 4, poorly graded gravel 6. They have to understand that these are the names according to the German standard, and that they have to do a classification. They have to realize that they have to go back to the sieve analysis setup, to their data sheet, and to plot the grain size distribution, as you can see here. And then they have to do the classification according to the German standard. They have to know how it works, and if they do it correctly, it will result in a poorly graded gravel. Back to this document, they see poorly graded gravel is assigned to the number of 6, and this is the number they have to enter in the circle. After one more task, they can calculate the solution code, which is 295 in this case. And with this solution code, they can open the lock and win the game. There are some challenges in implementing an Eduscape. For example, the tasks have to match to the content of the course and to the learning objectives as well. It's not always easy. Then we deal with purely technical content, and this has to provide an entertaining value. You all know that it's not particularly thrilling to read a standard or to apply a standard. So finding entertainment value in standards is not very easy. Then the tasks should not be too easy to avoid boredom, nor too difficult to avoid overload or frustration. We have several different students, and to find the way to find challenging but also solvable tasks for all students is not easy. Then we are confronted to limited resources and space, especially for large groups. That's not easy. By the way, I was very impressed by what ChatGPT generated when I asked him or her to generate this image, because it was exactly what I wanted to say. And last but not least, the design and also the support during the game, which is very important as well, is very time-consuming. But our experience up to now is that students enjoy playing the game, that students are highly engaged and intrinsically motivated, and that they appreciate variations in their everyday students' life. So we believe that EduScates enrich the traditional lab teaching and foster deeper understanding and engagement. I want to close with these last pictures of the EduScape of my co-author and colleague Ansgar, who is here as well. 3 years ago, we founded the Geotechnical Network for Innovation in Teaching and Learning in Germany, Austria, and Switzerland. And in February this year, we met at Ansgar's place to play through his EduScape. You see Wolfgang and René as well, they are here as well. And if you have questions on our EduScapes, feel free to ask us. Thank you very much.
Thank you very much. I'm very disappointed I didn't get to play my harmonica.
Me too.
So we have some time for questions, 1 or 2 questions. There's a question there.
Thank you very much for a very interesting presentation and initiative. I'm wondering, during the hour there in the EduScape, do you give any tutoring or zero? I mean, are they left by themselves, the students, to play? Or?
There has to be someone that helps when there are problems. If not, they are totally lost and it's a negative experience they have. So there must be someone and help if necessary.
And the background information, the theoretical information is anyway there by means of normal classes before they enter the room with all the questions that you will be present.
They had classes before and also laboratory course, and that's at the end of the laboratory course, they have the sum of all laboratory tests. Yeah.
So thank you, a nice presentation. I have just a question about the assessment of the students' work, especially individual ones and as a team. How do you assess their...
the assessment of the escape game.
How do you use it in the assessment of the students?
Okay.
In the course?
The students get a mark.
Yeah, it's embedded in the laboratory course at the final step, and they have to do it, but if they find the 295 or not is not the most important thing.
Okay, thank you very much. Thank you to Katarina. Next up we have David Airey, who will be taking us to the kitchen.
Okay, so good morning, everyone. Yeah, what we're going to be talking about is a COVID experience. It was a bit of fun I had. Well, maybe you won't think it's fun when I tell you what happened, but I think it was worth sort of sharing some of the things we learned. Okay, so I'm going to very briefly cover, why run with remote labs at home at all. And it's completely crazy, right? But anyway, we did it. How did we do it? And then just at the end, some reflections on what I learned from the experience. Okay, so just a bit of context. So this is a second-year introductory soil mechanics course. We have mostly second and third year students. Students are mostly doing between 4 and 5 years of a degree. The lab courses are integrated into the course, so we have 5 lab classes, and actually on the previous talk there was a list of all the common things. These 5 include 11 of those 15 or whatever were in this course. So there's a lot to get through. So it's highly regulated, which is one of the issues I'll come to at the end. So we have students in groups of 5. It means we've got 200 plus students. We've done it up to 350, I think. So there's very many lab sessions to make it all work. Because the students are doing all sorts of degrees, there's a lot of timetable restrictions. So it's not easy to change things. That's the important bit. Okay, the whole idea is to get the students to do hands-on. So this is my perspective. I'm an experimentalist. I think all the students need to learn about soil. They need to get their hands dirty, touch it, smell it, feel it, throw it at the floor, the ceiling, or whatever. It's part of the experience. To make it all work, and this is a previous conference, I've explained how we do it, but we have pre-lab material with videos showing the students how the labs work. They have to go through theory, there's a quiz, and in the lab itself they have a worksheet that they have to go through. And then, question about assessment earlier, basically the assessment is they have to complete the worksheet, get signed off at the end of the lab, that's it. But one of the students has to then write a formal lab report. So if 5 in a group, each student does one lab report. Okay, so confronted with COVID, and given I had such an incredibly complicated setup, why persist in trying to run the courses at all? Because most of my colleagues just cancelled all the labs. So hopefully, from what I've just been saying, I have a strong personal commitment to this. I've always run labs. Other labs have come and gone. Soil mechanics, my university, because of me, has continued every year to do this. I've been running the course for 35 years or something. Anyway, so there's, as we said, a well-developed resources to support it all, so that was all there. I didn't really want to change it. And when we had to make the decision, that everything had been timetabled. The students were in groups, they had this timetable. So, I could have just cancelled it. That would have been an easy option. But I was keen to have a go, take on the challenge of, well, how can we get the students to still get that hands-on experience? So just, one of the questions is why run lab classes at all? I just really want to flag here, I'd encourage everyone who's thinking about labs, the paper by Faisal and Rosa, reflecting a whole lot of work that was done in the US, published in 2005, about why you should have lab courses in engineering at all. So it's not just geotech, it's general engineering. But anyway, there's a number of objectives, and the ones in red are the ones that we were basically covering in kind of the standard geotechnical labs. Okay, so back to the more interesting bit, right? How to actually run the labs when the students are at home. So what's been done, remote labs have been done in many courses over many years, maybe not in geotech. But the standard approach is to get a kit that you mail to the students and with instructions, and it's all highly controlled. But we didn't have the time to do that. So that really wasn't an option. And also, as I mentioned, we had 200 students. So preparing 200 kits in short time was never going to work. Another approach, is virtual simulation. Many of you may have played with this. There's a few of them on the internet. But again, we didn't have time to do that. So what a lot of people did, of course, was to, video things, and indeed we did this as well, replace the labs with videos and some sort of demonstration. But that wouldn't have got you the hands-on, right? So I was really keen to do the hands-on, and so myself and my family had a bit of fun trying to do classification, compaction, flow, hydrometer at home, buying bits and pieces from local supplies and trying out various foodstuffs along the way. But that was the idea, what could I actually achieve using readily available equipment. So people could go shopping, they could buy things from the shops, there wasn't total lockdown, so they could get bits and pieces. And then some of the experiments, so odometer and shearbox, we really didn't have time to do anything about that. So we did videos and provided data. So everything was Zoom streamed live, okay? So all of these things I'm going to tell you is how I ran it. Okay, so I don't have time to go through. I mean, classification was more interesting, and there's a bit in the paper about it. But I'm just going to talk about compaction now. So need to remember that the students have actually done the classification before they did this. They kind of knew what they were doing when they got to this one. But the key thing was to find a suitable foodstuff. So rice flour was what I went with, because basically you could put it in the microwave and dry it out, and with a bit of care, you could measure a moisture content. So that was one of the key things the students had to do. Okay, water, they all had access to water. And electronic balance, I thought that would be a problem. I spent a lot of time playing with apps on mobile phones, which claim accuracy to 0.01 grams, but none of them worked. But it turned out that it wasn't a problem. They needed an oven, they needed a cup, and they needed some means of compaction. Okay, so you know, we went ahead, we did the experiment. Okay, so we have a worksheet, we're trying to follow through the worksheet. I didn't have time to modify the worksheet, so we're putting in the wrong numbers into the, but sort of the right numbers, but they're all the wrong, the quantities are all wrong. But into the worksheet, they did 4 compaction curves. They're all using rice flour. Most of the people were in Australia and they had the same rice flour, which made it easy. So I knew we had to start with 20% moisture content, the first one, and then 40, 60, 80, and we'd get a nice curve. I gave students the option of doing it with soil from their garden, and I think 3 students out of 200 chose that option, which surprised me actually, but it was good because it made it hard to manage when they did. Yeah, so the students plotted the compaction curve. We had the no air voids line. I had to tell them the specific gravity, okay, which was different from what it was in the notes and everything. So what could go wrong, right? So the rice flour. So, well, actually, let's go back to the microwave. So I had 30% of the students were international, were overseas, many of them in a hotel room somewhere. The surprising thing was that almost everyone had access to a microwave. I thought this would be a problem. I thought people might have to use an oven, but it turned out that everyone had a microwave, which was actually really good. But the biggest problem was the coffee cup. Okay, so, I mean, just a mug, right? I gave them instructions of what this container should look like, but people in China, they do not have mugs of any sort, right? So they were using completely inappropriate things to compact and use any force to compact it, like very delicate things or plastic, you know, takeaway food containers. So they couldn't really compact anything. So that was probably the biggest issue. The electronic balance was not an issue. To my surprise, everyone pretty much had an electronic balance that measured to 0.01 gram. Yeah, I mean, we didn't have one at our home, but all the students did. So yeah, maybe that's my age. Anyway, yeah, so the problem was that when they came to compact it, they didn't really know what they were doing, right? So they're just kind of gently tamping on the top. And I'm telling them to turn on their videos so I can see what you're doing. And they refuse to turn on their videos, right? That's one problem. And the second problem is when they turn on the video, they pointed at their face. And I said, I can't help you. Pointed at the experiment. And they still wouldn't do it. Okay, so it's frustrating. Anyway, they got the idea of what they had to do. They had to fill in the worksheet, and then they had to send it back to me. And the process was that we normally do. We sign off the worksheet that they've done the task, right? So the good students, okay, the good students could do this, and they handed it in almost immediately. The lab finished. The problem I had was the students who had no idea of doing labs. And this is where my first issue was the workload. So instead of having 40 groups of 5 who kind of got together and worked out how to fill in the worksheet, and we just signed them all off en masse and said, yeah, you know what you're doing. What I discovered, there was one student in the group of 5 who knew what they was doing, and then the rest of them I had to have correspondence with by email about, no, this is not right. And, you know, what have you done? You can't possibly have done this experiment. You need to do it again. And so this went on. It took 2 weeks to do this 2-hour lab because we were going backwards and forwards that you can't possibly have done this. So eventually we got them there, but obviously a lot of work on my part in just getting them to that point. Okay, so I've mentioned the issue with the videos. Yeah, so one thing was it was a one-off experience. I didn't want to change the worksheets, which obviously would have been good, right, if I'd have done that. And then the issue was, you know, we did first year in COVID, and I thought, oh, that's it. And then the same thing happened the next year. Again, without much warning, there was a complete, you know, lockdown. So, okay, I'm using the same worksheets again. I know this is no good. I know it's going to be a disaster. But we carried on, and so we did it for 2 years in a row. Okay, so the key thing for me was, you know, when we're doing the labs, the students tell me that, yeah, the labs help their understanding. But what I could see was that when I've, you know, made them do this on their own, and they had to show me, because they kind of couldn't escape, most of them did not really understand what they were doing. It was particularly the case with the classification, okay? But the compaction, even then, it was very straightforward. They still didn't really get it. So, you know, just filling in spreadsheets, which is really what I was, a worksheet, what they're doing, they're really, you know, that doesn't mean they've learned anything, right? That was what I discovered. And certainly not in the lab class, right? I mean, maybe because we had this extra backwards and forwards, a lot of them actually learned a lot more, but at the, you know, at the cost of me. So, I mean, so it leads to a question at the end, right, is, you know, I've spent 30 years getting this whole process to work with up to 350 students, getting them all through the labs because I think they're learning something. And now I'm reached the point of, oh, okay, but maybe a lot of them aren't actually learning anything like as much as I thought they were learning. So yeah, the previous talk was great. Maybe, you know, we need something like that to really get them to really, you know, appreciate what they're doing. Anyway, that's my talk. So, thank you.
Thank you. We have time for 1 or 2 questions. I have a question. Food items are often very relatable. Students know what rice or salt or whatever, and they're often a lot more consistent materials. So have you considered using food items to either speed up or improve the repeatability of your actual lab tests?
No, but we do have a clay. So we use kaolin, but it's a very permeable kaolin to do that, and we prepare them in such a way that, you know, so everything's highly regulated. We've got to have the right material. We pre-prepare stuff to make sure all the processes can happen in the 2 hours, right? Okay. Yeah, and we have odometers are 11 millimeters tall, so you know, things like that to make it work.
Yeah. And I also would like to say that maybe we are not having so many geotechnical engineers, but the ones are the best. Thank you very much.
All right. So our next presentation is by Bruno Paulo. And as educators, we're often asking for case studies. And Paulo has answered and is going to give us a few in his presentation.
Okay, I'm setting a timer. Good morning, everyone. So today I'm presenting on behalf of Mr. Okyay, who's the technical manager at our group, Afraneo. And we're going to address considerations into geotechnical engineering education through balancing, optimization, and sustainability. So a brief content overview, the introduction on what we mean by sustainability, strength, and durability. Then we're going to do a focus on a key point, which is settlement. We're going to address material choice as well. and then 2 case studies that put that into actual action and design. Our point is that strength, durability, and sustainability can be achieved simultaneously through design choices. So the overview, the goal is to, when designing, because we're speaking from the point of view of practitioners, we need to balance strength, durability, and sustainability. So we identify that there are traditional design approaches and which focus on technical performance and cost efficiency, obviously. And we can introduce additional focus points, which is performance-based methods and carbon footprint, for instance. So on the right-hand side, we have an image of 2 designs for a water tank, for water storage. On the left, we have what we would call a traditional design, which makes use of a concrete raft, which is stiff and heavy and durable, but is also material intensive. And on the right-hand side, we make use both of new materials and new approach. New materials because there's geosynthetics, which were not readily available maybe dozens of years ago, and this design tolerates more settlements as well. Our point, to go back to the point of this conference, is that education through project-based teaching and numerical modeling can help future practitioners to integrate these additional focus points. So as I said, there's one focus point, which is settlements. And for us, there's room for design experimentation. We go back to the traditional design, which is to build something that is a structure with low settlements, low displacements, so as to satisfy the structural needs that go with the design. That leads to high use of concrete and unnecessarily stiff designs. We take the example of retaining walls. On the left-hand side of the image, we have strong retaining walls made out of concrete that achieve durability, stiffness, but they're also expensive with high material use and can be unnecessarily tough, so to say. So taking this point of view and the focus on settlements, we can have different designs that are more flexible, less material intensive, and can be less expensive. That's one example with retaining walls, and now we're going to go with the case studies. The first case study is the rehabilitation of historical buildings in Paris. It's called the McDonald Warehouse Project. And the point was the goal of the project was to transform warehouses into mixed-use facilities. So you have on the image to the right-hand side on top, the existing warehouse, and at the bottom, the completed project. You'll notice that there were additional floors that were added, and there were issues and challenges with the bearing capacity of foundations. I'm going to go ahead and just show you the design points that we can see on the image. So here you see a cross section of the design, simplified cross section. You noticed additional floors that were added. And new structures in gray to the right-hand side. So the point was that existing piles were reused through diagnostic and control. And when needed, additional piles were used as well. And the existing piles, they were reinforced with high quartz pressure injections, commonly known as jet quartzing. Throughout this project, there was field tests, design validations, and real-time monitoring. What we can take away from this project is that the reuse of parts of the structure led to reduced material use through the reuse of large parts of the structure. Our case study number 2 is a settlement-tolerant foundation system. So we come back to the point made earlier about settlements. which is the design and build of a water tank for that was a water treatment facility. And the project for us started at the construction process, so when the contractor was chosen, and the goal was to change from a very stiff design, which is shown on the left-hand side, so thick concrete raft on piles, deep piles, to a thinner concrete raft that is being supported by shorter piles through an earth platform, which is typical of the rigid inclusion method. You see at the middle the dimensions of the water tank. It's quite big, and on the right-hand side the finished project. There was, of course, monitoring throughout the project. So the sensors used were settlement sensors and earth pressure cells. The graphs you see on the left-hand side is settlements against time, and on the right-hand side is stress distribution at inclusion head and soil through time. So through continuous monitoring of displacement and stress distribution, and through numerical modeling validation, we could assess that the design was working accordingly to the prediction. And the design validation was done through validation of the stabilization of settlements over time under repeated cyclic loading. The second thing that we take from this experiment is that since the stiffness distribution under the raft is more evenly distributed, there were a significant reduction in bending moment, 2.5 times fold, and a reduction in concrete use and CO2 use, which was achieved through the change in foundation method. So not only do we save material on the foundation part, but we also save material on the actual structural part. So it's a win-win for everyone in this case through allowing some settlements and some displacements. The conclusion is simple. It's our takeaway message. Less material can lead to more efficient solutions, and the few recommendations that we can make. So obviously the theme of this conference is teaching and education, and as practitioners, we've been students and some of us teach. We think that analytical tool can be introduced in courses for students to become accustomed to them. Case-driven teaching with real projects when possible is a way to highlight available choice in design options and to give the tools to the students. And of course, interdisciplinary collaboration to promote holistic approach can be introduced as well. As we see, it's a way to optimize the structures. So that's the teaching and education part, and the practitioner part is also simple, and people have been using them for several years, is to integrate new materials, and so we call it smart material use, to include observational design in the design process, and to promote sustainability as a design and performance criteria. And here, sustainability can be promoted in earlier stages to the client as a design criteria and as a choice criteria for his project. Not only cost, but also sustainability through different tools, carbon assessment, or existing tools. So that's our takeaway message, that sustainability is a guiding design criteria throughout every step of a construction or rehabilitation project. We showed both. That's all. Thank you for your attention, and I can take questions.
Thank you. We have a question.
It was very nice to see in case study 2 the comparison between the classic design and the alternative optimized design. Is this customary? Do you always do it in the industry, compare the classic design with the optimized, or this was an exception, or somewhere in between?
So the two are quite different, because the first one, Mr. Okyay, who I'm presenting on behalf of, was present in the early design stages. So he could suggest to the client to reuse parts of the structure. So that's in the very early design. And you could, at the very beginning stages, show different scenarios. One is to rehabilitate and do minor changes, and one is to redo completely. And you have a scope of options for the client to choose from. And the second case study, Mr. Okyay started to work on the project as a contractor. So there were minor design changes available. And here it's pure optimization. For instance, they did not build a flexible water tank as shown earlier in the presentation, because the design was already set.
Just a question from my side. So in teaching, it's good to have case studies that illustrate things, but often we're looking for case studies where calculations can be done. So how much of the raw data from these case studies is available for us as teachers to use? And we can partner with you to help develop them.
We need to check what we still have and to have the client's authorization. But for instance, these data, they might be available, settlement and stress distribution, and as well the calculations that were done at that time. So we can exchange information.
Okay. Thank you. Any other questions? I think with that, we'll let Paolo off the hook and welcome our next speaker to the stage. Next up, we have Vicky Dimitriadi, who's going to be speaking about retaining walls, but will also be giving us a lesson in geography and how to become international without going anywhere.
Good morning, my name is Vasiliki Dimitriadi. You can also call me Vicky, because I've realized that in the UK it's much easier to use Vicky. Today I'll be talking about an international coursework on the design of a retaining structure in a building competition. So it was a collaborative initiative between two universities. The first one is based in the UK, Edinburgh Napier. And I was working with my colleagues, Dr. Barreto and Dr. Leek, who is now based in Strathclyde, but at the time he was at Napier. And from the other side, we had Lucerne University of Applied Sciences and Arts, and colleagues, Dr. Arnold and Dr. Vogt. So I'm not sure how many of you might be familiar with the concept of a coil. So I'll be talking about coil and what it means, and also the concept of design, build and testing. I'll be taking you through the equipment that we used and the materials, because we are talking about retaining structures, so we used specific soil materials and easy to find materials in the lab and in the everyday life to build the retaining structure. I also have pictures. Unfortunately, my presentation was getting too big for the videos, but I do include a link at the end where you can access more information like videos and the project brief, so you can find all the information. And in the end, conclusions on lessons learned and student feedback. So COIL stands for Collaborative Online International Learning. It started at the University of New York initially. It has been a way of enabling students and academic members of staff from different countries to connect. And it presents various benefits for students because it is establishing global collaborations. It develops their various skills like communication, language, digital and intercultural skills. It also presents a lot of benefits for higher education institutions because it's a very cost-effective way to enrich programs of study and offer opportunities for global engagement. So I have included the link up here so you can find more information. The design, build, and test concept is basically what the title suggests. It offers a very holistic educational experience because students start from thinking about the design, planning the design, building and testing a certain type of structure or what they're building. And then it combines a lot of traditional theory, mathematical modeling, and aspects of engineering practice. So, in our case, between Edinburgh Napier and Lucerne, the focus of the coursework was to have students working in groups of 3 to 4 students, and we were always aiming to have a mixed groups of Edinburgh Napier-based students and Lucerne students working together. And the purpose was to design a soil-nailed, anchored, reinforced earth retaining wall to support a sandy backfill and the prediction of its failure. So students were asked to develop an accurate prediction of the behavior of their chosen system and give detailed information regarding soil, boundary and initial conditions, as well as the geotechnical and structural loading. Now, going into more visual things, focusing on equipment and materials. So you can see here the 2 sandboxes that were used. So this was from Edinburgh Napier, and you can see the dimensions in length, width, and height in this photo. And then this was the sandbox used in Lucerne, HSLU, and the equivalent, the respective dimensions. In both cases, we were trying to keep things the same as much as possible. So we were trying to keep the height of the backfill more or less the same. In terms of materials, I do have here the particle size distribution curves. So the black one is the Leighton Buzzard sand used at Edinburgh Napier, and the grey one is the gritty material used at Lucerne. And I'm summarizing here the unit weights of the 2 materials and angles of friction. Okay. In the following slides, I have chosen a few cases of what was constructed in the lab, and and their failure loads. So this is a case tested at Edinburgh Napier University, and it's a plywood with soil nails. So we used plywood of about 5 millimeters of thickness for the facing panels, and the 8 millimeter diameter, 20 centimeter length timber screws. The backfill was the sand, the Leighton Buzzard sand I showed you earlier, and we started loading the backfill area with load progressively, and we were increasing the load up until failure. In this case, we reached up to 130 kilograms with no failure observed, so failure had to be induced somehow. Then there's another case tested at Lucerne. The facing panel here is cardboard, 3 millimeters thickness, and there were 3 rows of 6 soil nails made of bamboo skewers. And the predicted failure load was a lot less. It was around 19 kilograms. Another case here, then the facing panel is again a standard cardboard, but here it was, we got a lot more inventive by using paper straws filled with spaghetti, and we attached them to the facing panel using Haribos. And the failure was at 120 kilograms, and it was basically due to pull out of the reinforcement elements at points of attachment to the facing level. So it was interesting to see. Another case here tested at ENU at Edinburgh Napier, it was a case of a gabion wall. So here we used chicken wire filled with marshmallows and standard rope as reinforcement. And there was, as you see here, a very flexible wall. It still managed to retain 40 kilograms of weight, but there was plenty of soil coming at the front. Here we have another case of a wooden plate with soil nails. So the wooden plate was quite thick, it was 10 millimeters perspex material with soil nails. Those were constructed with cord wrapped around wooden columns of the retaining wall using polystyrene balls as anchors. The target load predicted by the initial calculations of the students was 54 kilograms, but that was exceeded and failure was induced by the students in the lab. I do have a link at the end of my presentation that takes you to the TC306 GeoWorld space, where I have uploaded more material and a couple of videos from the testing. Generally, this part of the testing was a part of the students' coursework. We tried not to link it too much with actual marking because we do not want to put additional stress on the students, but the students were assessed based on their failure analysis, both at the starting level before building the retaining structures in the lab and also afterwards analyzing what happened and making specific calculations to predict the failure mechanism. Going into some lessons learned from this initiative, I do have to say this ran for 2 consecutive years between the 2 universities. Generally, it takes a lot of planning before rolling out this initiative because there's 2 institutions that are participating, so we needed to make sure that there is the same scope of work and that the initiative runs within modules that have similar learning outcomes and include undergraduate full-time students that are more or less on the same level. Like in this case, for example, we had students from 3rd and 4th year from the 2 programs, and there was the knowledge that the students had basic knowledge of soil mechanics before taking this coursework. Of course, the module learning outcomes need to be also aligned. For example, in this case, in Lucerne, we always had to include a retaining system with soil nails because that was in their module descriptor, so we had to be very specific. Also, we needed to have comparable numbers of students from the 2 institutions, and that, especially in the 2nd year that the program ran, was a bit challenging because at Edinburgh Napier there was a larger cohort, so we had to choose students in order to match the numbers from Lucerne. Also, as David pointed out earlier in his presentation, the interaction between students was also a struggle, and we had to sort of, lecturers from the 2 institutions basically have to force students to interact with each other, especially on an online setting where people tend not to turn on their videos. It was something that presented some challenges. And the last one, accurate estimates of construction materials. That was a very, very, very useful lesson for both the lecturers and the students, as there was a very nice case of a student who wanted to build his wall made from his own Legos, but came to the lab with not enough Legos to build the wall, so we cannot proceed to testing. So it was a very useful thing to learn. In terms of student feedback, I have just copied some feedback from students from the 2 years that the program ran. It was generally well received from students from both institutions. They managed to work well together even after the forced interaction. They had the opportunity to work in a new environment, to overcome language barriers, time differences, and be accountable for their team and their individual work. So as I said earlier, you can go on to this link here and access the supplementary material. You can find the project brief, a PPT presentation that includes more videos and pictures, and I think a couple of samples of student work. Thank you, and I'm open to questions.
Thank you very much. There's a question at the back there.
Hi, this is not so much a question as a comment. My name is Vina Ajmera. I run the student competitions in the Geo Institute, and one of our national events is a Geo Wall competition. And I'd like to encourage your students and the students from the other university to participate. It's very similar to what you're doing, but they can compete with it.
Thank you very much.
Question on this side here.
Yeah, so the workload, because this, it's part of their coursework. It's about 20% of the total hours required for the module. I do have to point out that at Edinburgh Napier, the models were built by lecturers and technicians due to health and safety issues and space restrictions. So the students were welcome to be in the lab during the construction, but they were not really had to devote time to build the models. And yeah, it's about 20% of the total workload.
I just have a question from my side. So with these design, build, test exercises, I'm often very envious of our structural engineering colleagues who can design things that fail at a particular load. Do you think we can get there with these type of structures?
Like in real life?
Well, in your paper, the loads that the students predicted and what they actually failed at were very different. So do you think we can get to a point where we can actually get that gap to be small enough that students can actually feel confident in the calculations they're doing?
Well, I guess, you know, especially from the lab measurement, so to speak, it also depends on, you know, the constructability of all the modules and how you perform the experiment. So many things can be measured, you know, slightly different, I suppose. And yeah, I'm not quite sure I'm answering the question, but...
Yeah, no, I just think maybe we need to sort of figure out a way to set these problems so that the students can actually do calculations that bear some resemblance to what actually happens in the lab. Instead of just doing calculations for the sake of showing they can do calculations.
Well, if I understand the question correctly, we were asking students to sort of reflect on the differences between the failure loads between their calculations in the lab and explain why. So we were trying to, you know, make them at least think about why the two things were different. Yeah.
Okay, I think that brings us to the end of this session. Am I handing back to someone or am I inviting everyone to lunch? All right, let's close the session and give another round of applause to all the presenters. Thank you very much.